Good morning, everyone. We'll get started. I hope you all had a great break. I think most of us had a great break, at least on Saturday. It's a fantastic day of football. In fact, I like to get a quick check at the time. It's 7:59 a.m. and Michigan still sucks. You guys supposed to say that? Okay. Hope you enjoyed the extended break. Now, 2 weeks from today, we're taking our final exam precisely at 8 a.m. Monday of finals week. So looking ahead to the final, I would start thinking about reviewing, especially the topics you're most worried about from our past midterms, from whatever it is that you can recall from earlier in the class. Wherever it is you think you're going to struggle the most, I would kind of start there, and I would go as early as possible so that you can hopefully relearn some concepts or restudy some concepts that then pay off later in the course. And hopefully you find that as you review some of the older material, you'll see that we have reinforced a lot of the things that we learned earlier in the course as well throughout the semester. The final exam is cumulative. It will be slightly heavier on the newer material. So a little bit less than half of the exam will be new material. So that's the rest of Chapter 9, Chapter 10, Chapter 11. We're going to skip the final section in Chapter 11, so we're just going to cover sections 11, 1 to 6. We'll skip section 7. And then we'll cover some select topics out of Chapter 12. We'll only spend probably about a lecture on Chapter 12, so we'll talk about those topics later. So that'll be about half the midterm, or excuse me, half the final. And then the other half of the final will be review questions from Chapters 1 through Chapter 9 and Section 6 in Chapter 9. So you're only going to see maybe 2 or 3 or 4 questions per chapter on the review chapters from earlier in the semester. So certainly focusing on the bigger aspects of those chapters, the main ideas will be helpful. There'll be some practice finals that we put up that you can use. If you haven't done a lot of the daily quizzes, I would kind of think of, review Chapter 1 or review Chapter 2 in a study session. And then maybe, revisiting the textbook, looking through some of the sample and practice exercises in the book, maybe going through, if you like, the end of chapter problems. If you haven't seen some of those, they might be useful. Daily quizzes are another source of problems if you haven't done those. If you have done all the daily quizzes, you want more problems, the end of chapters are probably where I go next. Every other question, there's an indicated, I think the red faced questions in the end of chapter problems are answered in the end matter, so you can at least check your answers on those questions. Okay, so with that, let's head into Chapter 11 this morning. I had put up some Chapter 10 review questions. We'll get to those at some point, either today or Wednesday, depending on when we finish Chapter 11's content. And then, so we'll review Chapter 10 at some point this week, possibly today. We'll see where we get today with Chapter 11. Okay, so Chapter 11 kind of continues our track from gases to liquids to solids. So obviously Chapter 10 was on gases, so Chapter 11 we'll discuss liquids. The very end of Chapter 10, we were getting at the idea at low temperatures, a gas will begin to condense. It just kind of depends on what the gas is, on where that condensation point's going to be. We know water boils at generally a higher temperature than something like H2 because hydrogen's a gas at room temperature. So we know hydrogen's going to have a boiling point well below room temperature. Otherwise, it would have been a liquid or solid at room temperature. Same thing with like helium. Helium has a melting point of like 4 Kelvin. That's negative 269 degrees C. So some substances really, really low, that's going to tell us something about the attractive nature of like 2 helium atoms with each other. That's going to kind of tell us that 2 heliums must have a very weak attractive force between them because they don't really want to stick together. So it takes a really low amount of energy. If you think of temperature as energy, as you raise the temperature of a, say, liquid or solid, you're giving the molecules energy to move and then separate. So once they have enough energy, they can then separate. And we're going to see here in this chapter that we can look at the type of liquid compound or the substance within a liquid and try to see what type of intermolecular forces are present within a liquid sample so we can get a sense of how weak or strong are those intermolecular forces that attract the atoms or the molecules together. So we'll try to get a molecular comparison of gases, liquids, and solids. We'll look at some properties of the intermolecular forces of liquids. We'll talk about some heat changes that accompany the phase changes from solid to liquid to gas. And then finally, we'll wrap up with looking at phase diagrams, just getting a diagram that kind of shows us at different pressures and temperatures what phases do we expect to find for different substances. Okay, so let's take a molecular view here. A good starting point is the halogen group, because the halogen group has all three phases within it. Fluorine and chlorine exist at room temperature as gases, as their most stable form, and then all the halogens exist most stably as diatomic molecules. So we have F2 and Cl2 exist as gases, and then the description of gases from chapter 10 would just be non-interacting particles. So there must be a weaker attractive force between chlorine such that it had broken apart from those attractive forces at room temperature and the chlorines weren't stuck together like they are in liquid bromine and solid I2. So in liquid bromine, there must be a stronger force that's holding those molecules together. Therefore, it's going to take a greater temperature. It's going to have a higher boiling point before the forces that attract the two bromine molecules together, or the bulk bromines all together, we're going to have to provide a higher energy, therefore a higher boiling point, in order to break those attractive forces. So the particles are closer together because they're experiencing forces of attraction with each other. And iodine, you can sense, because it's a solid at room temperature, must have an even stronger attractive force, because it's going to take even more energy to melt the substance and then boil it than even for bromine and compared to chlorine as well. And so we can see that there must be some sort of pattern to the attractive force between chlorine, bromine, and iodine, and that for some reason the attractive force must increase with size. So we're seeing here that the larger the molecule, then the stronger that attractive force. And that's one of the things we'll see for a particular attractive force, that it's going to increase with increasing size. And so then there's another issue that we have is, well, what if there's a built-in kind of charge? Some molecules like HCl have a dipole moment. Now, Cl2, Br2, I2, those are nonpolar molecules. So these don't have that built-in dipole. So these are all nonpolar because they have the same atom bonded to itself. So neither atom's developing a charge. But in HCl, we do have this built-in charge where chlorine's going to pick up a partial negative. It's more electronegative than hydrogen. It's going to pull the electrons in the bond closer towards itself. Hydrogen develops a partial positive charge. And so then you can imagine that HCl is going to have a stronger, perhaps attractive force due to this like built-in electrostatic force of attraction that we now have that the other molecules don't have. Now we're going to have to discuss a model for how it is then that I2 and Br2 have an attractive force, because they can find a way to create this dipole moment within the molecules. We'll show this on a later slide, but we'll see that the like two adjacent I2s almost have to shift their electrons around such that they create a dipole moment where the molecule doesn't originally have one to begin with. And so we're going to get a attractive force between HCl due to that built-in dipole moment within the molecule. And then, but the attractive force is actually relatively weak. If we think about ionic bonds, if we're thinking KCl, NaCl, the ionic compounds that are all solids at room temperature, that this attractive force is nowhere near as strong as like a +1, -1, or a +2, -2, because if you think about lattice energy, the lower the magnitudes of charge, the weaker the attractive force, the less energy it takes to separate. So we get a relatively weak attractive force. This is going to be much weaker than it is for like KCl or for calcium oxide, where we get those stronger attractive forces. And so then these compounds are solids at room temperature, whereas HCl actually still turns out to be a gas at room temperature. I don't know if you can predict, and it's not always going to be a question of, is a particular, just looking at a molecule, can you predict if it's a gas, liquid, or solid at room temperature? But we're going to try to get into comparing like groups of molecules and try to see, as we kind of compare two molecules, that this molecule here still happens to be a gas, but then maybe we can make a prediction with it versus like HF, and we'll think about that as we go and look at more molecules and more comparisons. So let's then take a step back and kind of look at more general types of compounds. Like LiF's an ionic compound, so LiF has this strong attractive force. Now that's an ionic bond, that's an ionic compound. And so ionic compounds have really high melting points and boiling points, slightly a topic of chapter 12 when we talk more about solids. But compounds that have ionic bonds are going to have a much stronger force of attraction, therefore it takes a lot more energy to separate. So think about melting is going to take those atoms that are kind of locked into place, but still not totally locked in. So if you're picturing LiF or any ionic solid at like room temperature, it's not like the atoms are perfectly still. The atoms still have to be moving, but they're just not liquid. They're not tumbling around each other like they would in the liquid. But if you provide enough energy, then all of a sudden the ions can like move around relative to each other. So you can have ionic liquids It's just going to take a really high temperature, and then you can boil off the substance at an even higher temperature. Now, metallic bonds are also very strong. Some of the times, so ionic bonds do vary in their, metallic bonds do vary in their strength. So not every metallic compound has a super high melting point, but some of them do. Like beryllium has one of the highest melting points and boiling points for a metal, and it's also one of the smallest metals. It's atomic number 4, so it's one of the smaller metals too, and it has a relatively high melting point and boiling point. We talked a little bit about, actually I'd say we talked a fair bit about how ionic bonds, you want the ions to be smaller, because when the ions are smaller, they have a stronger attractive force because they're closer together. It becomes kind of a kappa Q1, Q2 divide by D problem. If we can put those ions closer together, then you get a stronger force of attraction in our ionic compounds. So generally we're thinking positive, negative attractive force. So like if we're thinking ionic compounds, LAF, F- compared to Ca2+, O2-, the 2+, 2- have higher charge magnitudes, therefore it takes more energy to separate. But then if you make the ions smaller, you put them closer together, so then they also then experience a greater attractive force, takes more energy to separate. The same thing with metals. So metals have valence electrons. They're almost flowing through the entire structure of the metal. This is one of the properties we'll talk about in chapter 12, that metals generally conduct electricity because they have valence electrons that more or less flow through the entire solid structure. And if you remove an electron, they flow to replace it. If you add an electron, they move to get away from that electron. So you get conductive properties within metals, but the property of melting point and boiling point, you can think, oh, well, being small is good because we have electrons that are flowing around nuclear charges. And so if we can make that charge small, the electron is going to then experience a greater attractive force, or not the electron per se, but the two neighboring atoms are going to have a stronger bond because the electrons and the positive charges are smaller. So we're really impacting the D term here by seeing that we have a small metal that has a really high melting point and boiling point. This also then leads to like mercury. If you notice, mercury is a liquid at room temperature. Only mercury and bromine on the periodic table are liquids at 25 degrees C, but mercury is one of the, obviously it's pretty big. So in its group, it's the biggest metal from zinc, cadmium to mercury. And as we drop in size, you weaken that attractive force because the charge centers are bigger. There's not as much attractive force now because we've made the distance of separation now greater. So we've impacted this D term, made it greater, and we then weaken the attractive force of those two neighboring atoms. Therefore, we've lowered the melting point such that mercury happens to melt below room temperature. Cesium's very close. Cesium's like, its melting point I think is like 31 degrees C. So if room temperature were a little bit warmer, cesium would also be a liquid at room temperature, and also cesium's very large. Now, some things get confusing, like, well, why aren't we talking about francium? Well, there's not much francium. So francium, if you see the elements with the parentheses, that means there's really not much. We don't really have a characterization. We don't do experiments generally with large samples of francium. So, we don't really know francium's melting point. I don't know if anybody's ever had enough of it together to really characterize its melting point and boiling point. Same thing with, like the element under mercury is actually, I can never pronounce it, it's Copernicus with eum in the end. So it's like Copernicium, I believe is how you pronounce it. But that particular element, again, is one that we actually have to synthesize. It's not an element that naturally occurs on Earth. You have to synthesize it. So only small numbers of atoms of an element that are beneath mercury have ever been synthesized. That's why we don't talk about the elements predominantly like in that last 7th row of the periodic table too much. Okay, now let's talk about another interesting compound, diamond. Diamond just contains carbon, and graphite also just contains carbon. And graphite and diamond both have really high melting point and boiling points. And you might be confused at first and thinking, well, how can that be? Because they have the weaker covalent bond compared to the generally stronger, if you recall, ionic bonds are usually at least 600 kJs per mole, if not higher. The metallic bonds look to be pretty strong. The covalent bonds were in the 400 kJ per mole range, but the issue with diamond is you end up with a 3-dimensional lattice of carbon atoms coming at you in all 3 dimensions, and then it kind of continues. So you have carbons without, through the structure in 3 dimensions. So you end up with this like 3-dimensional array of diamond of a bunch of carbon atoms. So you have a tremendous number of covalent bonds that are all what we call network bonded. So we have covalent network bonding in something like carbon. So again, we'll talk about these slightly more detail in chapter 12. Honestly, we won't talk much more detail than what I just said here and kind of rehashing it, showing you a few more pictures when we get later into chapter 12. But the key is seeing that when you have either ionic bonds linked, in 3 dimensions, the atoms in a structure, really high melting points. When you have metallic bonding, generally high melting points. There's a few cases like mercury, cesium, or as you go larger in metal, you tend to drop in melting point. But most of your metallic bonds are pretty strong. And then you can have covalent network compounds like diamond, quartz does this, SiO2, glass. Those have really high melting points and boiling points because you have 3-dimensional arrays of covalent bonds. We'll look more at those. You'll see a few more pictures of things that are the covalent network bonding when we get to chapter 12. Now, when we get to things that have just intermolecular forces, where there's no covalent or ionic bonds linking adjacent molecules, then we're going to have weaker forces of attraction because we're kind of down to the molecules either having built-in charges, so smaller magnitudes of charge that are linking up, or they have to induce this dipole moment in themselves. So nitrogen N2 is nonpolar, so it doesn't have any built-in charges, really low melting point and boiling points. Notice those are in Kelvin. So the boiling point of nitrogen, 77 Kelvin. I think that's minus we could just do the math. 195 Kelvin, I believe is what that is, or 195 degrees C. So really low temperature in degrees C. I don't know why I'm guessing. We could just literally throw it into a calculator. So 77 minus 273, that's minus 196 degrees C. In terms of the boiling point of nitrogen. So compound doesn't have a very strong attractive force because it doesn't have a built-in dipole moment. It's a nonpolar compound, relatively small, so low melting point and boiling point. We kick on the HCl where we have that built-in dipole moment. We then have a similar sized molecule in terms of like molecular weight. So the molecular weight of N2 is like 28 grams per mole. HCl is like 36 grams per mole. So we're in the same ballpark of size, but notice we have a much higher melting point and boiling point for HCl because we now have built-in charges. So that's what you get with having some charges is you get a little bit more of an attractive force, and then it takes even more energy then to separate the molecules. Think of temperature as a measure of kinetic energy. So as you increase the temperature of a sample, you give the molecules more kinetic energy, they move faster. So kinetic energy, 1/2 mv squared, have more kinetic energy, then the molecules have a higher velocity. So they're moving around faster, and if they move around fast enough, they have such a weak attractive force, they can then separate. You can think about water boiling. As soon as water hits its boiling point, the reason why you see bubbles is water's breaking the surface. Water has such a weak force then at that temperature that the molecules are just breaking apart in bubbles into the gas phase. So that's, if you think of the appearance of something boiling, it's because there's a less force holding the sample together than there is for it to separate. So it separates and boils off and becomes a gas. Now what about HF? HF's an interesting molecule in a lot of ways. I usually have talked more about HF. I don't think I've really gone on, people say I ramble sometimes, but HF's a really interesting compound because it's a weak acid. It's not one of the 7 strong. So it's kind of like an asterisk, right? Because it's like HCl, HCl, HBr, HI are the 3 strong acids in the halogen group, but HF, this is a weak acid, but it's a dangerous acid nonetheless. In fact, if I had my choice of working with HF, HCl, HBr, HI, it would be HF that I would never work with. HF will eat through your skin, eat through bone. It's very dangerous to work with. It causes a cascade of reactions in your nervous system. It doesn't take very much of it to get on your skin to actually kill you. So it's a very dangerous compound to work with that I think it's very useful to know that even though you can write formulas and you can be like, oh, it's a weak acid, must be safe. No, just because something's a weak acid doesn't necessarily imply any bit of safety. So HF, very reactive compound, very nasty to work with. I would avoid it. But notice that it has a higher boiling point and a higher melting point than HCl because it's more polar. So HF has a greater development of charge. So we get a bigger negative charge. If we're comparing HCl and HF, there's 2 things good for HF. One is that the partial negative charge is going to be higher in magnitude because fluorine's more electronegative. If you recall, when we talked about dipole moment in chapter 8, HF had the higher dipole moment, it had the higher magnitudes of charge. HCl has a lower dipole moment and has the lower magnitude of charge because chlorine's less electronegative. So for comparing the partial negative on chlorine, it's a lower magnitude. But it's a double whammy for HCl because you're then putting a less negative charge on a bigger atom. So you're increasing the size. You want a small atom with a high charge. And so the smaller the atoms you can have with the higher magnitudes of charge should give a stronger attractive force between adjacent molecules. So you're going to end up with a stronger attractive force between the partial positive on hydrogen. Hydrogen's a really small atom, so that's good. We're putting a bigger positive charge on hydrogen as well. So we get a stronger attractive force between the H and the F and two adjacent molecules of HF. And so we're going to call that, we call that hydrogen bonding, a very special type of intermolecular force. So hydrogen bonding doesn't mean that hydrogen's like shared between the two Fs. It just is the attractive force between two adjacent molecules where the hydrogen's going to be attached to fluorine. Then we'll also see only two other atoms, O or N. So we have to have an H directly attached to fluorine, oxygen, or nitrogen to have hydrogen bonding. And that's actually our strongest attractive force of the three attractive forces we're going to see. We have dispersion forces. That's going to be the force of attraction in nonpolar compounds. And it's also going to be a force that any other compound has. And it's going to be, we'll see a slide that shows this a little bit more clearly. It's something called like an induced dipole moment. It's the two, like N2s don't have a built-in dipole moment. They don't have these built-in charges like HF and HCl, so they induce it. They find a way to like shift their electrons around to induce a dipole moment so they can have some magnitudes of charge that they're exchanging so that they can have an electrostatic attractive force. And then that's going to be weaker because the molecule has to induce it and it doesn't have it built in. HCl has a dipole-dipole force of attraction. That's good because it has a dipole moment, so it's a stronger force of attraction. So it's like you have a relatively weak force of attraction, a slightly stronger force of attraction for dipole-dipole, and then hydrogen bonding is like an even stronger dipole-dipole force where you're having a compound that is polar, but then also has a really small atom involved, like NO or F. So we have high magnitudes of charge on the smallest possible atoms. Okay, so let's take a little bit closer at the attractive forces. So this is a view of dispersion forces in a sample like helium. So helium's, at least in terms of simplicity, a good starting point because helium has two electrons. You can think of electrons spinning one direction or the other direction around the atom. And then you can kind of think two adjacent heliums have their electrons just in random locations. So if we take two adjacent atoms at any given moment in, say, a gas sample, say these two heliums are bumping off each other, it's a relatively high temperature gas sample. Well, the two electrons are kind of nowhere near each other. There's no built-in charge. There's no like stickiness to that collision. So that's one of those billiard ball type collisions we're talking about in the kinetic molecular theory of gases. Well, as we lower the temperature of a gas sample and the sample starts to, like the atoms start to get closer together, the electrons can start to kind of take on a position where they each kind of go to the same side of the atom, but opposite on two different atoms to create a dipole moment. So this creates a partial negative side, a partial positive side, a partial negative and a partial positive, and then we get that built-in attractive force, like a small electrostatic force of attraction. And so the electrons have to shift and move kind of in a coordinated fashion in order to sort of create this induced dipole moment. Now the issue is for helium, it's not going to do this until we get to a really low temperature where they bump into each other and it's so low energy that there's not much energy available to separate the molecules. If you think about it going the other way around, going to a really low temperature, like as close to 0 Kelvin as you can get, you have solid helium, you start to warm up the helium, you get to 1 Kelvin, it turns out the sample melts. So the melting point of helium is 1 Kelvin, so just 1 degree C above absolute 0, helium melts. And then you get to 3 more Kelvin above that, you get to 4 Kelvin, the sample boils. And so you have a relatively weak attractive force. The sample has enough kinetic energy, breaks free of that attractive force. But the electrons have to pair up where they are to induce a dipole moment. And so we often call this that induced dipole force. So we're inducing a dipole moment by the electrons kind of shifting their motion. Now, And then this is like a dipole picture of what that might look like. So we can create a positive and a negative side, so we have some built-in attractive force. Now, you can probably imagine having 2 electrons versus 10 electrons versus 18 electrons. The more electrons, the easier this is going to be for the electrons to pair up their motions to induce this dipole moment. So the induced dipole moment is directly proportional to size. It's really directly proportional to like the spread of the electrons, like how far spread out the electrons are. So you could say it really kind of depends on the electron density, which is maybe hard to picture, but it's like if you could have 10 electrons, that's better than 2. So neon's going to have a higher boiling point and melting point than helium. So if we're comparing helium to neon to argon to krypton, that we're going to increase the melting point and the boiling point from top to bottom here for that trend. Because we have more electrons, they're going to be easier to induce this dipole moment. Even though the atoms grow bigger, and we were talking earlier, generally bigger charges have weaker attractive forces, but we're going to induce bigger magnitudes of charge. So therefore, as we increase the size, this induced dipole moment is going to increase in magnitude. We're going to increase the size of the electron density. The atom becomes bigger, the electrons occupy more space, easier to push around, easier to induce this dipole moment. And so then this is the main trend too for F2 to Cl2 to Br2 to I2. As you increase the size downward, you also then increase the melting point and boiling point for that same trend as well. Now, it doesn't work like when you then look at lithium to cesium, you don't get the same trend because we're not looking at molecules. Like when you're comparing lithium to like cesium, you have to think, okay, lithium to cesium, this is a different trend because these are metals. Because these are metals, the metallic bonding's weaker with bigger atoms. So this trend decreases in melting point and boiling point as you grow larger from top to bottom. So you have to think, the trend of increasing size only works for compounds that are molecular. So we're looking at molecular compounds, and so the halogen group are all molecular compounds. The noble gas group are all molecular compounds. As you increase the size, you increase the melting point and boiling point. If you look at groups of metals that might have all metals, then they're going to depend on the metallic bonding trends, which is that generally smaller metals have stronger attractive forces. And it's actually lithium in that group that has the highest melting point and boiling point. And then cesium was the one we said was just barely above room temperature. Let's compare here then what it looks like if you have 2 atoms instead of 1. It's generally going to be better to take the electron density, spread it out. So if we can have the same molar mass and have, instead of 1 atom, like so take xenon. Xenon's very big in terms of molecular weight. Xenon's molecular weight is 131.3 grams per mole. So if we're comparing xenon's molar mass to other compounds that have that same or approximately similar molar mass, but if we could have the electron center on 1 atom versus like 10 atoms, it's going to be better. So the more atoms we can have, that spreads out the electron density. That's going to make it easier for molecules that have more atoms with a comparable molecular weight to spread out their electrons. So if we're comparing neon to fluorine, fluorine's a lot higher. 2 atoms instead of 1 is better. Argon to chlorine, again, 2 atoms versus 1, relatively comparable molecular weights. And then having 2 atoms better than 1. Krypton to bromine, again, 2 atoms better than 1. So if we can take a comparable number of electrons, comparable size molecule, there's a little bit of probably a slightly better comparison this way. Like compare bromine to xenon, because bromine to xenon probably have closer molecular weights to each other than krypton and bromine do. And notice that xenon is still lower than bromine. So 2 atoms, again, with a comparable molecular weight is better than 1 atom. So it's going to be easier for something like bromine having 2 relatively large atoms that are now separated compared to a single xenon atom, which maybe xenon 1 atom is bigger than one of the bromines, but we have 2 bromines. And so 2 adjacent bromines is going to be easier to induce a dipole moment. So if you have 2 bromines stacked on top of each other, easier to induce a dipole moment to get that partial positive, partial negative attractive force built in. Then 2 adjacent xenons, lower contact points, fewer regions for the electrons to pair up, so you have a weaker attractive force. So the more atoms with a comparable molecular weight, the better it is for attractive force. So we're going to increase the attractive force if we can spread the electrons out to multiple different atoms. This also works for comparing like isomers of like a hydrocarbon, where one hydrocarbon like N-pentane has 5 carbons, 12 hydrogens, all linearly connected. And so this formula, we would just write the CH3, CH2, 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 CH3. We might recall this from our nomenclature too. Like methane was 1 carbon, ethane's 2 carbons, propane is the 3 carbons, butane is the 4. Getting the hydrogen count then right is the other issue. So like if you had propane, you have CH3s on the end, CH2s in the middle. So this is C3H8 for propane, just for a quick review on naming some hydrocarbons. But for pentane, there's an isomer of pentane that just has a different arrangement of the atoms. We call it a structural isomer, where we have a central carbon and then we have CH3s off the carbon. So we have CH3s here. If you notice, that still has the same formula of C5H12. So that just means it's an isomer. So 2 different isomers are 2 different compounds that share the same formula. So an isomer of pentane is called, you don't have to know the name neo, but neopentane is what we call, like another name would be like tetramethyl methane is a weird name you can think. You just have 4 methyls on a single carbon. It would be tetrahedral too. You can think here, this carbon here should be tetrahedral. To review a little bit of 3-dimensional shapes, we have 4 domains. They should spread out in a tetrahedron. So we should get a tetrahedral carbon with those methyl groups. And within a ball structure, it looks kind of like the structure we've shown here. Now, if you're just predicting, now it's on the slide, you can kind of see, but if you're just like guessing which compound do you think has a stronger attractive force, do you think it's the N-pentane or do you think it's the neopentane? The neopentane has such a small contact point. Like it's going to be really hard for the molecule to tandemly shift its electrons to somehow end up with a strong partial positive, partial negative. So it seems like the more a structure is cylindrical, the worse that's, or spherical is probably a better word. The more spherical the structure, the worse. The longer it is, the better, because then we have all these contact points here where we can be inducing dipole moments. So we can create a bunch of partial positives, partial negatives throughout the structure, and have a strong attractive force, or stronger attractive force as a result. So neopentane has a stronger intermolecular force due to having more contact points. And so both these compounds have that induced dipole force of attraction. Neither compound would be very polar. The CH bond, not very electronegative in terms of that bond. So these compounds just share in having the induced dipole force. So the induced dipole force stronger when we have a more linear compound. So we have a slightly higher boiling point for neopentane than we do, or excuse me, slightly higher boiling point for pentane than we do for neopentane. Let's look at dipole-dipole forces. So some compounds like acetonitrile is the name of CH3CN. I don't expect that you know that name, but we use this as a solvent a lot in organic chemistry. And so CH3CN has this C triple bond N group. And that happens to be, I don't know if we would have predicted that to be so electronegative, that it's actually really strongly electronegative. You have the triple bond between carbon and nitrogen does a really good job of pulling that triple bond towards itself and adopts a relatively high partial negative charge. And then a sample of acetonitrile therefore has that strong built-in attractive force due to being polar. So this compound here is a polar molecule with a particular strongly polar like cyano group or the CN group. You'll learn more about functional group naming later, but you get this strong attractive force because we have built-in partial positive and negative ends of the molecule already that we don't necessarily have to rely on the molecule to induce a dipole moment in itself. So the molecule has already the built-in dipole, so we don't have to induce the dipole to get the attractive force, or you're going to have a stronger attractive force as a result. And then you still can keep that attractive force even in a liquid. So even if you have the molecules tumbling around each other, like momentarily they'll have an attractive force as they're bouncing off other molecules. So they'll be in like like conformations, if you will, or they'll be like moving around and experiencing those intermolecular forces as they're tumbling around each other. So it's only when you get to the gas phase that you break free of having no real strong attractive force between the molecules. So until we get to the gas phase, these molecules still experience their attractive forces. So both of these samples in the solid and the liquid, the adjacent molecules have that dipole-dipole force of attraction, but they also still have an induced dipole force. So sometimes we call it a dispersion force or an induced dipole force. So another word we use a lot is dispersion force for this, that even molecules that have dipole-dipole forces, they can still manage to induce an even bigger dipole moment. And you'll see some molecules have maybe like a polar group and a really long like nonpolar group. So the nonpolar group can induce dipole moments through induced dipole forces through the dispersion force. And then the polar group has its built-in charge, so you kind of get both within one molecule. So you'll see us break down for a given molecule, what type of intermolecular forces does it have? For like acetonitrile for CH3CN, solid liquid sample, the compounds, the adjacent molecules would be experiencing dipole-dipole forces and induced dipole forces, the dispersion force. They would not have hydrogen bonds though. So the hydrogen bonding intermolecular force requires us to have nitrogen directly bonded to hydrogen. So we don't have N directly bonded to H. There's H in the compound, but not directly bonded to N. So there's no H bond. So we'll look more at H bonding as well as we go. So we'll have a few slides on H bonding. But right now, let's just make sure we see that we wouldn't say that this sample contains hydrogen bonding forces of attraction. And then also let's remember that when we talk about hydrogen bonding attractive forces, we're not talking about there just being a hydrogen bond in the molecule. Like there's carbon-hydrogen bonds in this molecule. We have the three hydrogens attached to carbon. The hydrogen bonding attractive force is a special attractive force between adjacent molecules of a specific type, H bonded directly to NO or F. So let's talk a little bit more about that attractive force as we go. So right now, let's break down a comparison of a few molecules. This particular comparison compares 4 molecules that are all relatively comparable in molecular weight. And the reason why I want to compare molecules generally that are pretty similar in size is as we increase size, we increase dispersion forces. And we have a lot of things going on. If we just throw in a molecule here that happens to be much bigger or much smaller, we would have no easy way to quantify, well, how much increased dispersion force do you get compared to the dipole-dipole force? But we can easily compare when the molecules are the same size. So propane here doesn't have any electronegative atoms. It's going to be the least polar. If we throw an oxygen in place of the central carbon, that molecule's name turns out to be dimethyl ether. So dimethyl ether has a small dipole moment due to having the electronegative oxygen. So oxygen's trying to pull electrons in towards itself, picks up a partial negative. We have some built-in partial positives. And so that's good. And so compared to propane, that increases its boiling point. Not by much, and again, I'm not going to ask you to predict when does this force of attraction become so strong that the sample becomes a liquid. It would just be more rank ordering, that propane is going to have a weaker attractive force, therefore it has a lower boiling point due to being nonpolar and only having the dispersion force. But then dimethyl ether has the dispersion force plus the dipole-dipole force. Now, acetaldehyde, and again, this becomes a tricky comparison. I don't know if I would expect you to look at the actual bonding of a molecule from what we know at this point to predict that if you have this, what we call a carbonyl or the C double bond O, that it turns out that that's pretty good at pulling electrons towards itself. I was about to make that pus when it's a negative, but partial negative on oxygen, partial positive on the carbon. Our hydrogen's here. So we have a particularly big negative charge on that O. Again, I don't know if I'd expect that you would predict that negative to be bigger than dimethyl ether, but it turns out that that negative charge is bigger than it is in ether, and we get a slightly higher dipole moment. If I were to tell you that acetaldehyde's more polar than dimethyl ether, I would probably expect that you would then say, oh, well, it should have a stronger dipole-dipole force. So we look at the dispersion force in this compound, relatively similar. But then it has this stronger dipole-dipole force. So we get an even bigger dipole-dipole force than we did in dimethyl ether. And then I don't know what it is about the CN group. Maybe it's a triple bond, but the CN group's a really polar group. Again, I don't think I would expect that you have that memorized or would know that by prediction. But if I look at the dipole moment and see that it's more polar, that this is the most polar molecule, I would probably expect that the most polar molecule of the 4 would have the highest boiling point. So if you look, acetaldehyde was higher than the ether. And then the acetonitrile being the most polar has the highest overall boiling point here. And so rank ordering, we just have a stronger dipole-dipole force. We still have the dispersion force too, but then an even stronger dipole-dipole force. So an even higher boiling point. So you can kind of rank order, kind of thinking the more attractive force that you have, the higher the boiling point, the stronger, the more polar you can make a molecule for a comparable size, the higher the boiling point as well. Now let's look at hydrogen bonding. Hydrogen bonding is very important. In fact, most of you probably remember the name hydrogen bonding. We talked about this in biology class. You probably talked about this even early, before you even took chemistry classes in high school. But water, HF, and NH3 are almost off the charts in terms of their melting points, boiling points, compared to the other neighbors in their groups. But let's start with CH4. So let's get a glimpse of a molecule to start off our comparison with, and just to see what this table is trying to show us, because it's just comparing carbon to, right below carbon is silicon, so it's comparing to SiH4 to germanium H4 to tin H4. And those are all just in a group together. So they form the same type of compound. In fact, all four of these compounds here, these are all tetrahedral molecules because they're all things that have 4 atoms, no lone pairs on a central atom. So we end up with a tetrahedral molecule. And then because it's tetrahedral, the same atom in all spots, the electronegativity is not particularly high for any of these atoms in this group. These all have all these molecules are perfectly nonpolar. So as you go from CH4 to SiH4 to germanium H4 to tin H4, why does the boiling point increase? Well, it just increases because we're going to a bigger molecule. So as you increase size, you increase the boiling point. So what we're looking at here is boiling point just versus the molecular weight of the compound. So as you go from small CH4, low melting point, to big SNH4, neither one of those has a strong built-in attractive force with dipole-dipole forces. None of them have hydrogen bonding forces of attraction. You have relatively low melting points and boiling points. In fact, tin H4 is still well below room temperature. Room temperature is around 300 Kelvin. So then if you're looking at let's look at HF perhaps next, because we were talking a fair bit about HF versus HCl already. So we knew that this trend was kind of true here, that as you go from HCl to the smaller HF, more polar, stronger charges, we had a higher boiling point, higher melting point for HF. But then notice if you then say, well, what if I go to HF to HBr to HI? Why does this trend increase here? So why do we go up to HBr, which is here, and then this is HI? Well, that's because those molecules are bigger. They're just picking up a larger dispersion force. So dispersion forces become quite additive, especially when atoms become very large. And so as you go from HF compared to HCl, if we're looking at boiling point, HF is higher because of hydrogen bonding. We have dipole-dipole forces and we have dispersion forces. We have all 3 forces present within an HF sample. And then within HCl, we only have dipole-dipole force. We only have dispersion forces within HCl, no special hydrogen bond. You may be thinking, chlorine's very electronegative though. But if you notice, chlorine's not off the chart. Chlorine isn't off the chart compared to HBr or HI. It's not higher, and boiling point is not dramatically higher than those two. And so as you're comparing HCl, that HCl is lower than HBr, it's lower than HI. And this is just because of an increase. These also have dipole-dipole forces that are weakening as you go to the less polar. So the dipole-dipole force is weakening as you go through this trend, but the dispersion force is increasing. So you have an increasing dispersion force from HCl to HBr to HI. And it's that dispersion force on why you increase from HCl to HBr to HI. Now, with that said, can you see how, well, HF would have the weaker dispersion force, so why isn't it lower? It's because it picks up that extra H bonding force. So without us calling this force of attraction or noticing or kind of realizing, oh, it's fluorine being really small, that's really important here, and it's the hydrogen being directly attached to it, so hydrogen's really small too. Hydrogen adopts a really high charge, so we get this exquisitely high boiling point for HF that's really not part of the explanation, just comparing dipole-dipole force and dispersion force. So if we only had dispersion and dipole-dipole forces, we probably would have predicted HF would have been lower in boiling point and melting point than HCl. In fact, it's a lot higher. And it's because of that H bonding force. Water is even more off the chart. Now, why is water so special? Well, water is even higher than, this would be H2S. This would be H2 selenium. Just going down the oxygen group, hydrogen, tellurium. That the water to H2S is the same issue of HCl to HF, that you have hydrogen attached to a smaller atom that's more electronegative. So the oxygen in water adopts a partial negative charge because it's pulling electrons away from two hydrogens, and it's going to adopt a partial negative charge that actually can be even higher than fluorine's because it has two hydrogens it's pulling from. So like oxygen is like stealing from two H's, and so it could give it a very good negative charge, and we now have two hydrogens that have a positive charge. That's like even better than HF. So water goes higher than HF in boiling point, comparable molecular weight to HF, but goes higher because it has two hydrogen bonding sites instead of just one. And it has an atom that's just a little less electronegative, but it still is able to pull its electrons, get a big negative charge as well on this still relatively small O. So water has like the two good things going for it compared to HF. It has two hydrogens to pull from, so the hydrogens have two charges, and then it helps put an even bigger negative charge on O. Now you may be thinking, well, nitrogen should be even better because it has three, but it just turns out that at some point you had a give and a take, and nitrogen ends up being a little bit weaker because nitrogen is just not as electronegative in that trend. So nitrogen can continue the trend of having a third hydrogen bond. NH3 does have three H bonds, it's just three relatively weaker H bonds in HF or water. So HF 1H bond, kind of midpoint, boiling point, water, 2 H bonds, good, right balance of electronegativity, number of bonds. Nitrogen weakens a bit, but it's still off the chart compared to phosphorus. This would be pH3, and still off the charts compared to arsenic and antimony. Just going down the group from nitrogen, phosphorus, arsenic, antimony. Okay, so, but if you notice from like H2S to H2 selenium, H2 tellurium, we have this increase here, and this is just from the increasing dispersion forces. So dispersion forces can be quite additive. They can start to add up as we go to larger molecules. This is in fact why like hydrocarbons like octane, like this main component in gasoline, octane is a liquid at room temperature, even though it's a nonpolar compound, just because it's a big molecule. Compare a C8H18 to like a CH4. Well, CH4 is a gas at room temperature. It's really small. C8H18, very big, even though it just has a dispersion force, they become additive, and you have a strong attractive force as a result. This slide here, I was having this thought of, if you look at a snowflake, which we're going to get snow tonight, I don't know if you guys saw in the forecast, and maybe tomorrow morning you'll wake up and have a snowball fight. They're supposed to get like 1 to 3 inches tonight, so let's go snow. Really ruin the commutes in for anybody who drives in on Tuesday. If you're new to OSU, we almost never close, so good luck with ever getting a snow day here. But anyways, like if you look at a snowflake, the smallest flake, like part of the flake that you can see with your eye is, you know, I was looking this up the other day and I forget the exact number, but I think it was about 0.2 millimeters of like one of the flakes of a snow flake that you can see with your like naked eye. And then how many water molecules would there be across this like 0.2 millimeter like distance? So if you're thinking like how many water molecules could we fit across that gap, it's like hundreds of thousands. You know, it's like when you see a snowflake, you may be thinking, oh wow, this must be like 3 or 4 water molecules. No, it's like probably 10 to the 12 or 10 to the 14 water molecules in a single snowflake. So you're seeing a tremendous number of water molecules within a single snowflake. But you can think within any one of those sets, or within a small set of waters that you're looking at, they're all going to have that attractive force. They're all going to have that water having 2 hydrogen bonding forces of attraction per molecule. So each hydrogen has the 2 attractive forces. So each hydrogen in water can form 2 hydrogen bonds. And then another thing I wanted to point out is that the hydrogen is still attached to one of the water molecules. It's not really attached to the other. Like the intermolecular distance between oxygen and hydrogen in a hydrogen bond is about 1.8 angstrom. And then in the actual molecule itself, it's about 1.0 angstrom. So the hydrogen is not like going back and forth. The water molecule is still H2O. The other water molecule is still H2O. They're not really exchanging hydrogens readily with the oxygens. It's just an intermolecular force of attraction. And you can see that the intermolecular distance is a little bit higher for the H bonding site than it is for the actual covalent bond. So this is a covalent bond, and then this is a hydrogen bond. And again, sometimes we think that the hydrogen bonding force is like the H attached to the O in one of the water molecules, and it's the H in one water and its attractive force with the O in another water molecule. Okay. Which of these molecules here, if we're just looking at a list, can we pick out which molecules can have this hydrogen bonding intermolecular force of attraction? And the thing we need here is not just there to be the presence of N, O, or F, we need there to be the direct attachment of a hydrogen to fluorine. Since fluorine only forms one bond, like fluorine and halogens can only form a single bond with a partner, or at least in a stable sense. So like hydrogen's only gonna form one compound with fluorine that hydrogen bonds. So there's no other compound we can write between H and F. There's no second compound, there's just HF is the only H bonding example. The CH3F doesn't hydrogen bond because fluorine is directly attached to carbon in that compound. So it'd be CH3 and then F. So this here, we have to have fluorine directly bonded to hydrogen. So that doesn't count. We have the alcohol. Alcohols are good. They have hydrogen bonding forces of attraction. Maybe good for a lot of reasons, but one of them being hydrogen attached to water, or hydrogen attached to oxygen. So it's very similar to water, except where we just replace one of the hydrogens with a group of carbon atoms. So CH3, CH2 is an ethyl chain, so that's ethanol. And then we don't get the hydrogen bonding force in dimethyl ether, again, because we don't have O directly attached to hydrogen. So we have O attached to carbon, and so that's not good enough to have the hydrogen bonding force of attraction. The molecule is still polar, so we still get dipole-dipole forces of attraction within A and C. We just don't get the hydrogen bonding force of attraction. So we only get the H bonding intermolecular force in molecule B here. There's one slide I want to finish on today. Let's finish on this one here. And then we'll come back to a couple, like one of the things that we haven't talked about yet. But on this slide here, what this is trying to show us is if we're looking at an atomic gas sample like neon or argon, an atomic sample that's a liquid or solid, like liquid neon, liquid argon, within that sample, we'd only have the dispersion force of attraction because there's no built-in dipole moment. If we're looking at nonpolar molecules like N2, O2, H2, these molecules here, CH4, nonpolar, we only get the dispersion force of attraction. That's a weak force of attraction. It can become additive as molecules become bigger, but for small molecules, it's a weak force of attraction. Polar molecules without H attached to NO or F, we have dipole-dipole forces. And if we have polar molecules that contain N bonded to H bonded to F, or O bonded to H, then we get the hydrogen bonding force of attraction. We'll talk about ionic bonding next time. Let's wrap up with our quiz for today. Today's keyword is Kelvin. So that'll do us for today. Enjoy, well, we got 4 more lectures to go, so enjoy the rest of your Monday, and I'll see you back here on Wednesday.